We have a question here on moment of inertia. We are considering a thin disk of radius A whose surface mass density varies with radial distance given by this function. Sigma is equal to A plus BR. Here, R is the radial distance, A and B are positive constants. We are supposed to find the moment of inertia of this thin disk about the axis passing through its center and perpendicular to the plane, that is in kg meter square. Well, do you remember the answer for the moment of inertia of a thin disk with uniform mass distribution over the surface area? Yes, it is mr square by 2. M is mass, r is radius of the thin disk. And how did you get it? You considered differential elements, infinite number of them actually, all the way from center till periphery so as to construct the thin disk. And you consider the differential element to be thin rings of negligible width. In this case, we are going to consider differential elements once again, but the difference is that the mass distribution is not a constant. In fact, we are given surface mass density variation with respect to the radial distance. So the procedure remains same, except that this time surface mass density is a variable quantity. And then we obtain an expression for the moment of inertia of a differential element integrated within the appropriate limits and get the final answer for the moment of inertia of this thin disk about the axis in question. Let's do that. Here is the differential element for you of radius r and very small thickness dr. First, we will obtain the expression for the mass of such a differential element, and then we will look at calculating the moment of inertia of the differential element, and then we will talk about placing such infinite number of differential elements with varying radius all the way from center till periphery and thereby constructing the thin disk which is in question, and thereby that integration will give us the moment of inertia that we need. So let's start with the mass. The mass of the differential element is dm, which can be written as surface mass density into the differential element surface area. Now we know what is the surface mass density expression. It is A plus B R. What is the differential element surface area? It's going to be circumference multiplied by the thickness. Now, this is the area I need. So, it will be 2 pi r dr. What about the differential element's moment of inertia when considered about the axis passing through the center O and perpendicular to the plane of the ring? We can write it as DIO. On the right hand side, it will be mass of the differential element into the radial distance square. What do we need to do next? We have got an expression for moment of inertia of the ring, which is the differential element. To get the moment of inertia of the entire thin disk, we are going to place, like I said earlier, infinite number of thin rings like this with varying radius all the way from center till periphery. So, what are my limits? The limits for integration, of course. Let's interpret that. The radius of differential elements placed like that varies from 0 till a. The right hand side expression has to be integrated with respect to r. That's exactly why my limits are for the radius. Now, let me interpret the left hand side. What are my limits for the left hand side? When I start from the radius 0, how much moment of inertia have I theoretically accumulated? 0. So that's the lower limit. When I reach the periphery, when I'm done with the construction of the thin ring in this fashion, and thereby using this expression, when I evaluate the moment of inertia for the entire thin disk this way, when I reach the periphery, the moment of inertia theoretically accumulated will be IO. That's the higher limit or the upper limit. Now, the left hand side integration will give you IO minus 0. Now let's look at the right hand side. dm is A plus BR into 2 pi R dr. All right, and there is an R square. So I have to include that here as well, and that will make it R cube. All right, let's simplify this expression. We have got 2 pi sitting outside, and this integration is with respect to R. All right. Now, let's integrate. We will get, for the first term, A into r to the power 4 by 4. For the second term, B into r to the power 5 by 5 within the limits, of course. Now, substitute the limits and simplify. You get 2 pi into A into small a to the power 4 by 4 plus B into small a to the power 5 by 5 after substitution. You can further take small a to the power 4 outside, and what is left here is capital A by 4 plus BA by 5. So, this is the moment of inertia required for the thin disk about the axis passing through the center and perpendicular to its plane. This is your final answer. The correct option for this question is A. We have here two wires. One is made of steel, another is made of copper. What are the length and cross-sectional area of steel wire? It's given as 4.7 meter and 3 into 10 to the power minus 5 meter square respectively. Now, what is the length of copper wire? Initially 3.5 meter and the cross-sectional area is 4 into 10 to the power minus 5 meter square. It is said that when you apply the same load for both these wires, the stretch in both the cases will be same. With this information, we are supposed to find the ratio of the Young's modulus of steel to that of copper. Well, let me help you in visualizing the situation first. Here is the steel wire, originally of length 4.7 meter, and here is the copper wire, originally of length 3.5 meter. If you apply the same load, what do you mean by that? These two weights are same in magnitude. When you do that, the stretch in the wire number 1, delta L1, is found to be equal to delta L2, the stretch in the second wire. This is the data given to us. We are supposed to find the ratio of Young's modulus of steel to that of copper. How do you do that? You take the definition of Young's modulus of elasticity. How do you define it? Well, you take it as the ratio of stress to strain. What is stress? The force applied divided by the area of cross section. What about the strain? It's the ratio of change in length of the wire to the original length of the wire. Now, if you take this definition and look at the Young's modulus of steel, that is the first case, you can write Y1 to be F1 by A1 divided by delta L1 by L1. Do we have the data for some of these quantities? Yes, we do. We can call the applied load to be F in magnitude. We don't know that. It's okay. What is the area of cross section of the first wire or the steel wire? 3 into 10 to the power minus 5 meter square. Now, this will become L1 by delta L1. L1 is known to us. It is 4.7 meter. Delta L1, keep it as it is. It's all right. Call this equation number 1. Now, let's look at the copper wire and see what is its Young's modulus like. With the given data, we can evaluate the Y2 to be something like this. F2 by A2 divided by delta L2 by L2. What is F2? The load applied. A2 is area of cross section for the copper wire. Delta L2 is the stretch that happens in the copper wire, and L2 is the original length of the copper wire. When you substitute the known values, what do we get? F2 can be written as F itself. A2 is given to us. It is 4 into 10 to the power minus 5 meter square. And this will be L2 by delta L2. L2 is known. It is 3.5 meter. That divided by delta L2. If you take the ratio y1 to y2, or equation number 1 by equation number 2, we get y1 by y2. That's what we want, isn't it? So, y1 by y2 turns out to be 4.7 divided by 3 into 10 to the power minus 5 into 4 into 10 to the power minus 5 divided by 3.5. And if you simplify this, you get approximately 1.8. So the ratio of y1 to y2 turns out to be 1.8 is to 1. That's your final answer. The correct option for this question is D. Let's have a look at the data given in the next question. We are considering here a steel wire whose one end is fixed to the ceiling of an elevator, which itself is moving up with an acceleration 2 meters per second square. There is a load 10 kg attached to the other end of the string. And the area of cross section of the wire is given to be 2 centimeters square. And we are supposed to find the longitudinal strain produced in the string. What else is given to us? Acceleration due to gravity 10 meters per second square. And the Young's modulus of steel is given to be 2 into 10 to the power 11 Newton per meter square. Alright. Let's visualize the situation first. Here is the wire, originally of length, let's say L. When you apply this load, and when this elevator is moving up with an acceleration 2 meters per second square, it can be seen that the wire stretches by a small amount, and let's call that delta L. What do we need? The longitudinal strain, which can be defined as the ratio of the change in length in the wire to the original length of the wire. How do we find this? What comes to our help? It's the definition of Young's modulus of elasticity. It is defined as a ratio of the longitudinal stress to the longitudinal strain. We have defined longitudinal strain already. Let's look at longitudinal stress. It is defined as a ratio of the restoring force produced in the wire or the tension produced in the wire under these circumstances to the area of cross section of the wire. If you call the restoring force as tension or T, then it's going to be sigma equals T by A. Now, with this definition, we can write Y for the wire to be T by A divided by delta L by L. What do we need? Delta L by L. So, delta L by L turns out to be T divided by A into Y. We are given the cross-sectional area of the wire, and we also know Y, the Young's modulus of steel material. But we don't know what is T, the tension in the string. Let's find out. We can consider a free body diagram for the mass here under the given circumstances and apply Newton's second law of motion and find tension in the string. How? Well, for the mass M, which is hanging here, consider an observer in the elevator frame itself. Remember, elevator is moving up with an acceleration 2 meters per second square. So this happens to be a non-inertial frame of reference. If you are considering all the forces acting on this mass, then you have to account for the pseudo force felt by it as well. Now, there is gravitational force acting in the downward direction mg. Remember, this lift is actually moving up with an acceleration 2 meters per second square. So the pseudo force considered will be in the downward direction, and that will be ma. What is A? A is 2 meters per second square. The tension in the string attached to the mass will be in the upward direction. So T happens to be m into G plus A. Let's substitute. We get delta L by L to be m into G plus A divided by A into Y. Now, substituting the values, m is 10 kg, G is 10 meter per second square, A is 2 meter per second square. What is capital A? The cross-sectional area of the wire is 2 centimeters square, or you get 2 into 10 to the power minus 4 meter square. So, substituting that, Y is given to us as well. It is 2 into 10 to the power 11. If you simplify this, you get around 3 into 10 to the power minus 6. That's your answer for the longitudinal string, or the ratio of change in length in the string to the original length of the string. The correct option for this question is B. We are considering an ideal fluid. What do you mean by an ideal fluid? Something which is incompressible. And this fluid is flowing in a pipe in a streamline flow. Okay. The pipe has a maximum and minimum diameter of 6.4 centimeter and 4.8 centimeter respectively. With this given information, we are supposed to find the ratio of minimum to maximum velocity of the fluid inside the pipe. All right. If this fluid is really incompressible, then we can consider the fact that the volume flow rate of this fluid inside the pipe must be a constant. What is volume flow rate? The volume of the fluid that goes through the given cross-section of the pipe per unit time. And how can you write it? Product of A and V. What is A? Cross-sectional area of the pipe considered. And V is the speed of the fluid at that cross-section. And this product must be a constant. In that case, if you look at both the ends of the pipe given to us and call the cross-sectional area here to be A1, the speed of fluid flowing through the pipe to be V1, then on the other side, the cross-sectional area to be A2 and the speed of the fluid here to be V2, we can write that A1 V1 must be equal to A2 V2. That's your equation of continuity. What is the interpretation of this? The volume inflow rate must be equal to the volume outflow rate. In other words, the volume of the fluid entering the pipe on one end per unit time must be equal to the volume of the fluid flowing out per unit time at the other end of the pipe. But you also notice that if A into V is a constant, if A increases, V reduces and vice versa. Since A1 is higher in magnitude compared to A2, we can conclude that V1 has to be minimum in magnitude and V2 will be maximum. So, we are considering V minimum by V maximum, and applying the equation of continuity, we can write A1 into V minimum equals A2 into V maximum. We need this ratio, V minimum by V maximum, and that turns out to be A2 by A1. What is A2? It is pi into D2 square by 4, where D2 is the diameter on the other end. That divided by A1, which can be written as pi into D1 square by 4. Let's simplify this. Pi will get cancelled, 4 will go away, and we get V minimum by V maximum to be D2 by D1 whole square. What is D2? 4.8 centimeter. And D1 is 6.4 centimeter. Take the ratio and square it. If you simplify this inside, it will be 3 by 4. Square it, you get 9 by 16. That's the ratio you need. The correct option for this question is B, 9 by 16. We are considering a cylinder of height 1 meter which is floating in water at 0 degrees Celsius with 20 centimeter height in air. Now, if the temperature of water is raised to 4 degrees Celsius, the height of the cylinder in air becomes 21 centimeter. It has increased. We are supposed to assume that the expansion of cylinder is negligible and that the cylinder stays vertical. And with this data, we are supposed to find the ratio of density of water at 4 degrees Celsius to density of water at 0 degrees Celsius. All right. Let me help you in visualizing the situation. Here are the initial conditions. The temperature is 0 degrees Celsius. The cylinder stays vertical and is in equilibrium. What do you mean by vertical equilibrium? If you add up all the forces using the sign convention along the vertical direction, they add up to give you 0. The net force acting on the cylinder along the vertical is 0. That's what it means. Now, which are the forces acting on the cylinder in the vertical direction? One is a weight in the downward direction. Another is a buoyant force acting on the cylinder in the upward direction. What is its weight? Its mass into acceleration due to gravity, which can be written as the total volume of the cylinder, Vs. S stands for solid, all right? Rho S is density of the solid cylinder and G is the acceleration due to gravity. So, this is weight. That must be equal to the buoyant force acting on it. What is it? It's a weight of the displaced liquid, which is water at 0 degrees Celsius here. How do you write that? You write it as Vf into rho F into G. What is Vf? The volume of the cylinder immersed in water at 0 degrees Celsius. That into rho F, the density of water at 0 degrees Celsius, into G, the acceleration due to gravity. Now, if you cancel G on the either side, you get a ratio of rho F to rho S to be equal to Vs by Vf. Now, what is Vf? The total volume of the cylinder. Vf is the volume of the cylinder inside the water. Do you see that if this is 20 centimeter, this is 80 centimeter, and the total height of the cylinder is 1 meter. So, the ratio of Vs to Vf turns out to be simply 1 meter, or you can write it as 100 centimeter divided by 80 centimeter. Call this equation number 1. Let's keep it aside. In fact, for the next condition, we need this, so let's write it on one side. Rho F by rho S turned out to be 100 centimeter by 80 centimeter. Okay. Now, we are looking at the increase of temperature, and the final temperature is 4 degrees Celsius, and the height of the cylinder that stays outside the water happens to be 21 centimeter. Why? It's because of anomalous expansion of water. When you increase the temperature of water from 0 to 4 degrees Celsius, does it expand or contract? It contracts. Thereby, the volume of the water reduces, the density of water increases, and it facilitates more and more height of the cylinder to stay outside the water. That's exactly why this became 21 centimeter. So what is it inside now? 79 centimeter. And the total height is 100 centimeter. Even for these circumstances, you can look at vertical equilibrium, and the net force acting along the vertical is 0. So, the weight of the cylinder is balanced by the buoyant force on the cylinder in the upward direction. But let's be careful. The volume of the cylinder inside the water is not the same. So, let's call it Vf prime. And the density of water is also not the same. It's at a temperature of 4 degrees Celsius and it has changed. Let's call the density of water at 4 degrees Celsius to be rho F prime. So Vf prime into rho F prime into G will give you the buoyant force acting in the upward direction. Equating them, we get this equation. And let's find the ratio of rho f prime to rho s from here, which is Vs by Vf prime. What is Vs by Vf prime? Isn't it simply 100 centimeter by 79 centimeter? What do we need? With all this data, we are supposed to find the ratio of the density of water at 4 degrees Celsius to the density of water at 0 degrees Celsius. In other words, we need rho f prime divided by rho f. How do you get it? Take the ratio of equation 2 to equation 1. You get rho f prime by rho f to be 80 divided by 79. And if you simplify this, it happens to be around 1.01. That's your final answer. The correct option for this question is A, 1.01.